Welcome to a lesson with Dr. Powell. Let's take a look at how to take the derivative of a vector valued function. Now, let's use r here, and this function will depend on a variable t, so it'll represent a path through space. I could write it in different ways. I could write it using this notation, or and maybe I have different functions here, x of t, y of t, z of t. For instance, maybe I have 2t plus 3, maybe cosine of t, and maybe 2 sine of t or something like that for these different components. That's one way of writing this vector valued function. I could also write 2t plus 3, I, borrowing it from quaternions, and this is very common. And often we use a little symbol here to represent I as a vector here in the x direction, plus cosine of t, j, plus 2 sine of t, k. Okay, so I could represent my vector valued function in such a way. Now, let's look at, after having this, what it means to take a derivative. Well, what is this? Think of this as the tip of a vector. I mean, r is a vector in standard form coming from the origin, and it's changing. And it's changing where the tips follow a path, just like this. Now, to take a derivative, we kind of do the same type of thing as we normally do. We add a little bit to the input, we subtract what it was before we added to the input, and divide over by the run, h. So we're taking a derivative with respect to the input, or the parameter t. Visually, let's think about what this is. Suppose that this is r of t right here. Suppose this is r of t plus h here, just a little further off. Now, if we were to subtract this, notice that this is vectors, and we're taking a limit of this as h approaches 0. So a limit of a difference quotient. Now, notice this is a difference of two vectors. Difference of these two vectors would just be this vector right here, which looks almost tangent to the curve itself. In fact, as these points get closer together, it actually turns out to be the vectors that we get the limit in direction to be tangent to the curve. Very tangent to the curve, okay? And so when we take this limit, we're actually going to end up getting a vector out of it, and I'll call this v at t here. And it's going to be tangent. In fact, it's going to represent velocity. Quite literally, we're taking the limit of the change of position divided by the change in time, if you think of t as being time. So you could think of r as position and v as velocity, and it interacts just as well if we think of this in terms of vectors and vector subtraction. Now, how does this even work? Well, remember that vector subtraction happens component-wise. So we're just subtracting in the relative components and then dividing by h, which distributes over everything, and we're taking limits in each component. That just simply amounts to taking a derivative in each component. So to take the derivative of a vector valued function amounts to simply taking the derivative of each respective component. So in this particular case, the derivative would simply be just the derivative of this part, which is 2. This part right here, which would be negative sine of t. And this part right here, which would be plus 2 cosine of t. And we were just successful at taking the derivative of this vector valued function. Thanks for watching.